Hi everyone, I'm Stephen from TCS Research. This work is on predicting sentiments in image advertisements using semantic relations among sentiment labels. This paper is co-authored by Manasi, Niranjan and Shirish at TCS Research. So, understanding the sentiments evoked by advertisements is crucial in serving them appropriately to consumer. Advertisements often use images to evoke sentiments. An image can convey multiple sentiments of different nature. Automatically predicting these multiple sentiments can help serve better advertisements to consumer, especially in an online scenario at scale. In our work, we have explored a neural network model based on graph convolution to predict such sentiments, which exploits the semantic relations among sentiment labels. We use it to predict multiple sentiment labels using an annotated dataset of 30,340 image-based advertisements. We also find a distance metric that best represents the distribution of the sentiments in the dataset and utilize it in the loss function that separates the applicable sentiments from the non-applicable one. We report an improvement in mean average precision and overall F1 score over a multi-modal multitask state-of-the-art model. So let us explore why this is important. There are typically two ways in which ads are served. One, where you know about the user through the browser's history and product purchase history, etc. So if a user is interested in adventure and tourism based on such history, you would serve an advertisement with adventurous, joyful like sentiments as shown. The other scenario is where you do not know much about the user, but we know about the content that is consumed. That is, we are aware of the context of the advertisement. For example, a user is reading an article on tourism. You may serve an adventurous ad such as Mountain Dew one. But consider that the user is reading an article on adventure tourism in times of COVID-19. Now the Mountain Dew advertisement, which also has another sentiment associated with it, such as joyful, feels out of context. Instead, you might need another ad which has a sentiment of alert or caution along with adventurous. This shows that we may need to understand multiple sentiments with respect to an advertisement so that we can persuade the user in a right context. Inferring emotions from an image is not a trivial task. There have been efforts to understand the emotions from the images. One notable attempt is Deep Sentibank. It is a model trained on images collected from the web that are tagged with multiple sentiments. The reported detector's performance on natural images is noteworthy. There were efforts by Hussein extending the Deep Sentibank to advertisement image and found that Deep Sentibank performed poorly in terms of accuracy. It was also observed that a detector trained on natural images could not be generalized to advertisement images. There were many other efforts to predict the sentiments. The recent one was by Zhang. Zhang proposed a novel deep multi-modal multitask framework to integrate multiple modalities to achieve effective topic and sentiment prediction simultaneously for advertisement image understanding. In our work, we try to address certain aspects that are missing from the previously proposed sentiment prediction framework. As observed by Peng, an image can evoke emotional ambivalence in a viewer. For instance, the image advertisement shown here conveys both shock as well as the calm emotion. We observed this aspect throughout the advertisement dataset proposed by Sen, where on where one image was tagged by 3 to 4 sentiments on an average. In a general setting, to solve the advertisement sentiment understanding problem, pairwise semantic relation between the sentiment labels has been typically neglected. In our work, we have done some analysis on the label space to come up with a method to exploit the pairwise relationship, which I will be discussing in few minutes. Accompanying this, we also have used the context of the advertisement by employing graph convolution network. Before proceeding to the analysis, I would like to walk you through the dataset so that you can get a clear idea on how it looks. The dataset compiled by Hussein et al. Contains 64,140 advertisement images annotated with topics and sentiments and action reason pairs. Out of this, only 30,340 are annotated with sentiments. Some examples of advertisements are shown here. Each of these 30,000 images are annotated with at least one representative sentiment. Besides, the dataset also groups together semantically close sentiments to a representative sentiment as shown. Each advertisement in the dataset is annotated by at least 3 raters and at most 5 raters. This brings us to the discussion on the analysis of the label distribution. The figure The figure shown here is the count of the image advertisements in the dataset against each representative sentiment label. The obvious fact here is the distribution is heavily skewed towards certain labels. In particular, I am pointing out to creative label. We have done multiple experiments on this observation, and I'll discuss that in few slides from now. Now, in connection with semantic relationship among the sentiment labels, our idea is to analyze the sentiment label space of the dataset and find out the best metric that can optimally represent the data. All the 30K images are annotated with 115 sentiment labels. Out of these, 30 sentiments are representative and rest are all semantically related. To find the best metric that can best fit our data, we have used unsupervised technique to analyze the sentiment label space. Firstly, we employed agglomerative clustering with the number of clusters being 30 and linkage set to average. Using this method, we clustered the word embeddings for the 115 sentiment labels with 15 widely used distance metrics. We observed that the maximum distance metric best suited this purpose based on two parameters, namely sentiment label clustering and data perplexity. The ideal case for the first parameter is the sentiment label clustering as shown in the figure, where each representative label also with its semantically related label is clustered together. The same can be observed from this plot here. There are 30 clusters with minimum of 6 sentiments and maximum of 6 sentiments and minimum of 1 sentiment per cluster. And once we use agglomerative clustering with L2 norm, this is how the clusters are formed. Here, most of the labels fall into one or two clusters, which is not very optimal for us. And this plot here is using max norm. This is better than L2 norm clusters formation. From this comparison, we can clearly observe that L2 norm performs poorly when compared to max norm. Though max norm's cluster formations is semantically weaker compared to original clusters that are formed, that is the best we have in our hands right now. So the second parameter is the data perplexity. It is the image count annotated with more than one semantically different sentiments. So the ideal scenario for the second parameter is that the number of image per cluster must be close to the dataset's image count per cluster as shown. From these plots, we can observe that the max norm's first, second, third, and fourth peaks are close to original peaks than that of L2 norms. From these insights, we are convinced that max norm distance metric suits best to represent all the labels in an optimal way. So we choose max norm to formulate the loss function in our model. We employed graph convolution neural network to exploit the semantic relations between the sentiments of the advertisements. We also used the model to learn the semantic relations in the context of visual advertisements. The graph convolution neural network operates on graphs. G is equals to A dot protected with X dot protected with W, where A is the adjacency matrix, X is the input matrix, and W is the weight matrix. The nodes in the graphs are configured with word embeddings of the sentiments. As shown in the architecture, we first learned to project the d-dimensional feature vector extracted from the convolution neural network into the sentiment label word embeddings to contextualize each sentiment with the advertisement. The pairwise similarity between the contextualized sentiments was computed to learn the semantic relations between each sentiments in the context of advertisement. We opted to capture the pairwise similarity between the nodes along with the semantics of the sentiments in the context of an advertisement with the adjacency matrix. W here is randomly initialized. After the graph convolution computation, overall model loss is computed over resultant graph. Based on the conclusion on the distance metric I explained earlier, we employed hinge rank loss with minor modifications in terms of norm as shown. The loss function can be interpreted as the average norm of the resultant graph multiplied with all positive labels that act as threshold to penalize the violation caused by the negative labels. To explain further, if the max norm between the resultant graph and a particular negative sentiment label from the set is less than the average max norm between the resultant graph and a positive sentiment label, the system will be penalized by the amount of violation. The total loss is proportional to the total amount of violation for the negative labels for an advertisement and is summed up and backpropagated. We have used annotations of each advertisement in the dataset as positive sentiment labels and regarded the rest of the sentiments in the sentiment label space as negative sentiment labels. The matrix P in the shown equation contains the word embeddings of positive sentiment labels. Similarly, the matrix N contains word embeddings of negative sentiment labels. While training, we have provided an extracted feature vector from ResNet 152 for each advertisement image as an input to the model. After graph computation, matrix G is provided as a response by the model, and the same is plugged into the loss function to train the model end to end. During inference, let us assume that S as a column matrix of all 115 word embeddings of sentiment labels. We matrix multiplied the model's output G with S. The resultant matrix, when norm, gives the distance from the origin to every sentiment label. By sorting the resultant matrix of distance in ascending order, we obtain labels that are closest to the origin. The top k of these labels can be considered as predictions for that specific image input image, k being the number of sentiment labels of an advertisement. We have used mean AP and overall F1 score to evaluate our model. To compute our scores, we have used the scikit-learn's multi-label evaluation implementation. We have performed multiple experiments on this setup. I would like to present some experiments that we used to benchmark and also showcase some important observation. Firstly, we have used the whole dataset with no undersampling strategy. This is experiment number 1 in the table shown. Secondly, we have found the mean of the distribution and sampled all the labels randomly, which are about 2 times the mean. By doing the aforementioned, the frequency of the creative label was reduced to 40% of the original frequency in the dataset. This experiment was repeated 5 times and is reported as experiment number 2. As shown in the table, the mean AP and F1 score of experiment number 2 has improved over experiment number 1. As I have spoken earlier, this improvement was all after removing 60% of the creative label. On further examining the F1 score between the experiment number 1 and experiment number 2 explicitly for the creative label, the drop is just 1.4%, which is relatively negligible. This shows that the undersampling creative label did not show any considerable difference in the score. However, the improvement in overall F1 score from the experiment number 1 to experiment number 2 indicates that there is an improvement in individual F1 score of all other labels by removing the creative label, and the same was manifested during our analysis. From this, we can infer that the creative label negatively influences the performance of the other labels. Investigating further, we removed the creative label completely from the training and validation split of the dataset. We also removed the 3 semantically similar sentiment labels, creative, invented, and productive, from the embedding matrix. We trained the model on the mentioned data and tested it on the original test dataset containing the creative label. This is basically experiment number 3 as shown here. Experiment number 4 is similar to experiment number 3, but the only difference is that we held back the word embeddings as they are. We did not remove creative and its semantically related words from the embedding matrix. The test data for all the experiments is the same. From these experiments, we observed that there is a 60% drop in F1 score from experiment number 1 to experiment number 3 while inferring the creative label. Whereas from experiment number 1 to experiment number 4, there was a drop of 11%, which is relatively less. The 46% improvement of F1 score from experiment number 3 to experiment number 4 as shown indicates that the semantic embedding space plays an important role and should be explored further. Our best results are obtained with undersampling the creative label, that is with experiment number 2, which is an improvement of 14% in mean AP and 4% in overall F1 score, or the state-of-the-art model that was mentioned. Last but not the least, as aforementioned in my presentation about the label space analysis and distance metric in the loss function, we benchmark mean AP and overall F1 score using the standard L2 norm based loss function until the model reaches its optimal capacity. Later, we extended the same to the proposed loss function using max norm. The plot between mean AP and F1 score here shows that the distance metric proposed concerning the loss function contributes significantly better to the overall model performance, as it consistently outperformed the one based on the standard L2 norm. We attempted to understand the effect of the efficiency matrix on the overall model performance. This is basically for the evaluation study. We unplugged the efficiency matrix A from the architecture that I explained and recorded the mean AP and overall F1 score for the first 5 epochs. Though the difference is not noticeable initially, as the training progressed, we found out the model to perform better with the efficiency matrix at higher epochs. Secondly, we attempted to find the effect of randomly installation of embedding matrix E as proposed by Lee. Initializing E with word embeddings is one way random installation. We found out that the installation E with embedding matrix showed a 3.6 improvement in mean AP and 7% improvement in F1 score. Through these experiments, emotional ambivalence could be captured up to some extent, at least in the context of image advertisements. We believe that we believe that extending the sentiment labels to larger pairs with semantic relations using word embeddings may find utility in annotating advertisements with correct multiple emotions. As we have shown, with limited experimentation, the semantic embeddings of the unseen label in our model, even in the absence of the training data, can help in predicting these labels. In future, we are planning to extend our work on unseen labels to practical use cases using zero-shot learning. Thank you.